Hello everyone, welcome to my channel ML Guru. In this video we will see the concept of regularization and we will see how to use it to reduce overfitting or the problem of high variance. So first let us understand the problem of overfitting. So on the left side you can see this is our original data which we had used to demonstrate the concept of underfitting and overfitting. Then in the second figure, you can see the red line, which was our prediction, which was nothing but a 2-degree equation or a quadratic equation, whose equation is written down here. And we saw that this equation was the ideal fit for our data. And in the third figure, you can see when we fitted a 4-degree equation on this data, we faced the problem of overfitting, meaning it was doing good for all the training points, but it was doing bad on the test points. Now look at this 4-degree equation. What if I set the values of this W1 and W2 to 0? What will happen? As you can notice, it will turn out to be a quadratic equation which will be same as this one. So when we set the value of W1 and W2 is equal to 0, in this particular case we will get a quadratic equation which will be ideal fit. Of course this W3 and W4 parameters and the bias will be trained so that it will fit the data, and since it is also quadratic equation it will also be an ideal fit. But I have explicitly set the values of W1 and W2 to be equal to 0. So now let's see how this model by its own can set or reduce the values of this weights such that the problem of overfitting is solved. The concept here is that we are trying to convert a high complex function into a simple function. As you can see, this 4-degree equation was very complex for this data, or it had a freedom of flexibility such that it can overfit on training data. But by converting this complex model into a simple model, we have reduced its freedom of flexibility so that it cannot overfit on training data. It will generalize the overall data. Okay. Now let's see how we can train our model to do this. So here was our original loss function, which was the mean squared error loss, and this was our motive. We want to set the values of W1 and W2 to 0. Now let's modify our loss function to this, and you can see what I have done is I have added two terms here, which is uh, a huge number times W1 plus another huge number times W2. Now the objective of the training is should be that the loss function should be minimum as possible. Okay. Now to minimize this loss function, what will the model do? The model will set the values of W1 and W2 close to 0 such that these two big terms will get 0 down, so that we are left with this original thing. But by doing this we have reduced the value of W1 and W2, and we have also simultaneously reduced the complexity of our model. Okay, so to minimize the loss we have to set the values of W2 and W1 to 0. But in general we will put this parameter lambda, which is a hyperparameter, and the value of lambda, for example here we set the value of lambda to be 1000, but in general we can put any value we want. And here as you can see we did this for just W1 and W2, but here we will do it for every term, every weight term. And another thing which you can notice is we are putting the square of the weights. Okay. Now There, by doing so, what will happen is there will be a trade-off between reducing the magnitude of these weights and minimizing the squared error loss. So it must not be the case that it will reduce all our weights to zero. It will reduce only that particular weights by which the complexity of our model will reduce, and also the squared error loss is not ignored. Okay, and this uh, concept is known as L2 regularization. And instead of adding this lambda to the square of the weights, if we put the absolute value of these weights, it is known as the L1 regularization. Most of the case L2 regularization is used because when we use L1, what happens is it is seen that the model sets most of the weights, the unnecessary weights, directly to zero. So it does a kind of like feature selection between this uh, x power 4, x power 3, x power 2. But we don't want to force the value to be zero. Hence we use this L2 regularization, in which it will not force the value of the weights to zero, but it will reduce to a small number close to zero. Now let's see regularization in action. What I have done is I have set the degree to a 6-degree equation, and as you can see initially it was overfitting, but as we increase the value of lambda, the regularization increases. And also notice the training and test score. So let's reset it. Okay, so you can see the training score is 1, but the test score is very bad. And as we increase the value of lambda, the regularization increases, and the complex model slowly becomes an ideal model. Okay, now let's look at this hyperparameter lambda. So when the value of lambda is equal to 0, which means this whole term is zeroed down, so we are left with the original loss function. So in that case there is no regularization. So ideally the value of, if we want to solve the problem of high variance, if we are facing overfitting, we have to set the value of lambda greater than 0. Alright, when you have high value of lambda, which means high regularization, so we are increasing the bias. So above certain limit, if we further increase the value of lambda, it will go from high variance problem to high bias problem, which is underfitting. So we should not go above a limit. Okay, and if we have low value of lambda, which means it has low regularization, so we have to set the value of lambda accordingly, and we will see further how to choose the best value of lambda. So for that, what we have to do is we have to divide the dataset into train and test. The test part is also called as validation. Ideally it should be called as validation. Now what we do is we train the model on different values of lambda. So initially, suppose we were facing the problem of overfitting, in which we had let's say lambda somewhere around here. So in the overfitting, as you know, the train error is low, but the test error is high. So what we do, we increase the value of lambda, and as the value is increasing, you can see the test error is falling down, which means it is performing good on the test data as well. And obviously the training error will increase because initially it was overfitting, but we want that our model should generalize the overall data, the training data as well as the test data or the validation data. So when we increase the value of lambda, the training error goes up, the test error comes down, and after a certain limit what happens is the training data continues to go up, the training error continues to go up, but the test error which was coming down will also go up. Why? Because now we are going towards the high bias problem. Okay, so we must stop at this particular point. So that's it in this lecture. In next lecture, what we will do is we will apply all these concepts to solve a project. It will be an end-to-end project, right from data pre-processing to hyperparameter tuning to deployment. See you in the next lecture. Thank you.